Okay, now we're going to use matrix approach to solving systems of linear algebraic equations. So say we've got these three equations and these three unknowns, x1, x2, x3. Satisfy yourself that this matrix equation is the same as these three scalar equations. Do this scalar multiplication, I'll get 2x1 plus 6x2 plus x3 equals 7 at the top, etc. So now I can look at this single equation of matrices that actually represents three scalar equations and three unknowns, ax equals b. So that's how we can convert this equations into matrix format. And we're going to be talking a lot about the augmented matrix, which just means we tack on B as the right column of a matrix. So this here would be the augmented matrix representing this system of equations. Okay. Now we want to use matrix methods to solve that system, but to get there, we need to talk about Gaussian elimination. And the operation is called row reduction by a series of row operations to get a matrix into row echelon form. These are the three operations. I can interchange two rows, I and j. And so you can follow what we do. I have symbology for each operation. So if I'm just switching rows, I and j, that's what I call it, bars of ij. I multiply, okay, another operation is multiplying any one row by some constant. So if I multiply the ith row by the constant c, I indicate it by this, c times parts of r. And the third operation is multiplying a certain row and adding it to another row. So let's say I multiply the ith row by c and add it to the jth row, parts of j, and I replace the j row with that result. Convince yourself that those three operations are really, I could do them by a matrix multiply. Switching two rows, say rows 1 and 2, I would multiply the matrix by this matrix. If I just want to multiply row 2 by c, I'd multiply it by this matrix. Last operation would be multiplying by this matrix. So if I started out with a system like this, ax equals b, if I do the same operations, row operations to each side, I still get an equality. That kind of concept is useful in that row operations preserve things. So let's talk about Gaussian elimination. What we're trying to do is manipulate a matrix to get it into row echelon form, which I defined in a previous recording, by doing a series of row operations. So let's try to follow this. Let's say this was our starting matrix. And by the way, this applies to any matrix. It doesn't have to be on the augmented matrix. But here we're starting with the augmented matrix that came from that original series of or system of algebraic equations. So let's see. There's no unique way to go through this, but you want like ones up here at the top left, and you kind of want to gradually make these things below it 0. You kind of want to move it into row echelon form. So the first thing I'll do is real simple. I'll just switch rows 1 and 2, because here's a 1. If I switch them, I'll have a 1 up here. That's all I did there. Switch rows 1 and 2. Now the top row is -1, -1. Second row is this row. All I did there. Now I would like to get rid of this too. I'd like it to be a 0. So I'll subtract off twice row 1 from row 2 and replace row 2 with that. So I'm replacing row 2 by subtracting twice row 1 from it. So I get 2 minus 2, which gives us a 0, which is why we did this. 6 minus 4, 1 minus a minus 2 or plus 2, 3. 1 plus 2 is 3. 7 plus 2 is 9. That's all that happened there. Now I'll do the same kind of thing to get rid of this 5 or to make it a 0. I'll subtract 5 times row 1 from it. So 5 minus 5. 7 minus 10. Minus 3, etc. Do that arithmetic. And now I want this guy to be a 1, so I'll just multiply that row by a half. Starting to get there. Now I want this guy to be a 0, so I'll add 3 times row 2 to it. So minus 3 plus 3 makes that a 0. What did I say? 1 plus 9 halves, 11 halves. So I start getting some ugly arithmetic here. But I've made pivot points the way I want, and I've got zeros down here at the bottom. Now I'll just multiply this bottom row by over 11 to make this guy a 1. There we go. This guy is now in reduced row echelon form. So that's what I just did here with Gaussian elimination. As you do more of this yourself, you can do multiple steps at once. There's no unique, correct way to do it. But generally what you're trying to do is one's kind of going from top left to bottom right and get zeros below that. So you kind of work your way down from top left to bottom right. Some students almost do things randomly and it doesn't make sense. But now this matrix represents the same system of equations in the same variables. So I can go the other way. I'll take this matrix and write what its corresponding scalar equations are. This just means x3 equals 5. This means x2 plus 3 halves x3 equals 9 halves. So I can just back substitute. This gives me x3 directly. Now substitute it into this equation and do that arithmetic, and I have all 3 variables. x1 equals 10, x2 equals minus 3, x3 equals 5. We call that one solution. It's all 3 variables, but it's one solution, all 3 simultaneously. I could keep doing row operations to try to get it into reduced row echelon form. That process is then called Gauss-Jordan elimination. So if this is where we started in row echelon form, now we want this 3 halves to be 0. So I'll subtract 3 halves row 3 from row 2. Place row 2. That's that operation there. What will I do also? I want this guy to be a 0 also. So I can kind of do 2 operations at once here. I'll add row 3 to row 1 and replace row 1. This is the result. I won't go through all that. In this case, if you finally got it here, this is reduced row echelon form. Now you can just read off the answer without doing that bag substitute algebra or arithmetic. x1 equals 10, x2 equals minus 3, x3 equals 5. I don't find this to be labor saving. I tend to just do the, I'll just do the back substitution. It's as easy or easier than this. That's Gauss-Jordan elimination. That was a case of we got exactly one solution. It was a square matrix. Well, A matrix was square. We did another example and came up with this as our augmented matrix. This tells us that x1 equals 7, x2 equals -1, and 0 equals 0. We actually have an infinite number of solutions here. In this case, x3 could be anything and it still works. As long as x1 is 7 and x2 is -1. What we do there is we use a parameter. Let's start with t. And we'll just say in this case, x3 equals t. And we have one free parameter. Here's how we express that infinite number of solutions. T can be any number. What about this guy? We don't always have to do square A's. The same number of equations is unknown. We can do other possibilities. So this is 2 equations and 1, 2, 3, 4, 5 unknowns. So yes, we're going to get infinite equations. This says that, let's see, x3 minus x minus 6, x4 minus 6, x5 equals 4. Those are the only true constraints there. The rest of it, we're free to pick. And this system has 3 free parameters. I'll call them T, U, and V. I'll say x1 equals T, x2 equals U, x3, well, I'll say x4 equals V, and x3 has to maintain this same relationship. So x3 equals 6 times quantity V minus 1, and x5 has to equal 4. So here's a way to express the solutions to the system. I have 3 free parameters. They can range over the entire real line. Students got in trouble if they ever expressed any x variable in terms of other x's. That's what your original system of equations does. That's not solving it. You need to put it in terms of either numbers or these free parameters. No x's to the right. To the left, and to the right. So now we've got a third possibility. So far, we've had exactly one solution, an infinite number of solutions. What about this guy? We did all our Gaussian elimination. We came up with this augmented matrix in row echelon form. This bottom equation. The top one says x1 equals 7, x2 equals -1. We have 0 equals 1. It's impossible. This system is inconsistent. Inconsistent. It has no solution. 0 solution. So those are the 3 possibilities. And here's some examples of augmented matrices in row echelon form. This guy has exactly one solution. x1, 2, 3 equals 7 minus 1, 1. This guy has an infinite number of solutions. x1 is 7, x2 is -1, and x3 can be anything. And this guy has no solutions. Those are the 3 possibilities. Exactly 1, an infinite number, or 0. That's basic linear systems of algebraic equations and Gaussian elimination.